So, what do you remember about the equation of a line from grade 10? An equation of a line, y equals mx plus b. So, this works out good for 2 dimensions. If you had to do something similar for 3 dimensions, you could do that. The problem is there doesn't have to be a y-intercept in 3 dimensions. So that kind of is a problem for y equals mx plus b. Also, we've talked about slope is rise over run for 2 dimensions. And in 3 dimensions, you have like a rise, a run, and what was the other R letter we made up? The reverse. The rise, the run, and the reverse, whatever that means. So there isn't a nice acronym for that either. So then we need to start looking for other ways of writing an equation of a line that works well for 2 dimensions and works well for 3 dimensions. And that's the vector equation of a line. So here in blue, this is my line. And every time you have a line, it is in some way can be represented by saying if I take the origin as my starting point, then I can say where a line is based on reference to that origin. And the idea is if you take any point on that line, so here's a point A, then that point A can be represented by the vector OA, which is a position vector. And you take another point on that line, C, and that can be represented by its position vector, OC. Now, this line is going in this direction. This is the direction of the line. Either that way, or I could put the arrows the other way. That's the direction of the line. Now, that's a vector as well. AC is the direction of the vector. So what we're going to do is we're going to say that this line, this whole line, can be the same as take a point to start with and go as far or as short as you would like to in this direction. So for example, if I wanted to get to the point R, I would just have to go a portion in that direction, and then I would get to the point R. So the equation of a line will look like this. Any point R. So here's any vector R. Any vector R along that point could be found. So here's my vector R. Any vector R on that line could be found by first taking a vector that's on that line, a position vector. Like point A can be represented by the position vector A. And then if I go a certain amount in the direction of AC, I will get to the point R. If I wanted to go further, I could go, if I wanted to get to this point, which is twice as far, then T would be 2. If I wanted to go backwards to find another point on that line, then T would be negative. And so this is the idea of a vector equation of a line. And we'll do some more examples and it'll help us see it even more. Yes, Connor?
What exactly is the quiz going to be up to?
The quiz for Thursday will be up to whatever we get done today. I don't think I won't put equations of the line on there, so up to here. Because we won't get, we've got 5 minutes left today, so yeah.
You said like R
Mm-hmm.
is the same as point A plus some amount
Of the direction. So here, let's erase what we've got here. So this vector R is the same as going, because that's on the line, right? It's the same as going to A. That's what this part is. Plus, now I want to go this direction a certain amount, and I'll get to R. If I picked another point on the line, let's say I'll do it in a different color. Let's say this point, this vector here. If I wanted to get there, I could go to A and then go along this direction further, and I would get to that point. And any point I pick on the line can be done that way. Go to A first, then turn yourself in the right direction, and go a certain amount in that direction, you will get to that point. And all those points put together make a line, and that's why we call it a vector equation of the line. Yeah, instead of having a y-intercept, you just have a point to start with. Now, this point has many different possibilities. It doesn't have to be possibilities. It doesn't have to be the y-intercept. Like y equals mx plus b only worked with the y-intercept. This one, you could have chosen the point C instead. Can you see if I wanted to get to R and I had chosen the point C instead, I could first go to C. And then this is my direction vector is still the same, but now I would have to use a negative value to get back to R. And what would change is this value of t. Depending on the point you have, t's would be different, but it would still give you the same line. So we write it like this, r equals a plus tb, where b is your direction vector. So we're going to be talking about that a couple times. That's your direction vector. You start with any point on line. So this A can be any point on the line. And this is the direction vector that you're going. And again, you know how when you figured out slope, it didn't matter if you chose one point as your first point and the other as your second. You'll get the same slope as if you switched them around. Same thing happens here. For finding your direction vector, if you picked A first and then minus C, you would get the same direction, just in the opposite way, but it'll still give you the same line, because the line has to have positive and negative directions from the point you're starting with. Then once we have our regular equation of the line, okay, the vector r is some point. It's got an x-coordinate and a y-coordinate if we're thinking in 2 dimensions. It'd have an x, a y, and a z if we were thinking in 3 dimensions. And the point A has an x-coordinate and a y-coordinate. And the direction vector has an x and a y, saying how many do you want to go for your run and how many do you want to go for your rise. So from this, we have 2 different equations, because this is our r, this is our vector r, this was our vector a plus t, and this was our vector b. So the parametric form is saying, just look at your x-coordinates. If I just look at my x-coordinates, then x is equal to this, and this gets multiplied by t. So I get x is equal to a1 plus t times b1. And if I just look at my y coordinates, my y is a2. This b will also get multiplied by that t. And this is called the parametric form. If you take this form even further, because when we did y equals mx plus b, there was never a parameter t. But if you take this further and solve for t, then you're going to get the Cartesian form. And this is where we'll start next time.